Yeah, it's John Black here again. I just want to go over a couple of things from the last video about the Minkowski diagram. Here's another example of it. Um, Here would be the time axis. Here would be one spatial dimension, x-axis, and the speed of light. We fix it at a 45-degree angle. But this shows more of it. I only showed one quadrant before. This is all four quadrants. If you can see that the light goes through all of them. You know what I mean? To form this triangle on the top and the bottom. Um, this is a two-dimensional graph. Obviously, if it was in three dimensions, these would be cones. You'd have a upper cone and a lower cone. And just to let you know that these where the red is, where the lines are going horizontal, those are the only places. If you start off here at 0, 0, time and x, those are the only places you have access to. This is your past. This is your future. And always remember, your vectors can never be like any of these vectors, because look at those vectors. Those are all pointing downward. And if you point it downwards, that means you're going back in the past, and you can't go back in the past. At least we don't know how. So everything from your start point, which this is now right here, this is now. All this down here, that's your past. That's the only part of your past you can get. You can, like this point right here, you can never get to that. Never in your past or your future. Same here. All these dots that are outside. Now this is your future. That's your only possible future. The reason why is because light can't go faster than the 45-degree angle, and light goes as fast as anything can go. Okay. C, that I'm not exactly sure what C stands for. I'm going to say it stands for causality, because that's what C is. I mean, that's what the speed is, 186 miles per second. It's the speed of causality. I also wanted to go over this space-time interval. This is basically the same formula kind of as in the last video. You can see up on top, this right here is your space-time interval. Now it equals, I have these actually mixed up, but in the long run it won't matter. And I'll tell you how I messed it up. I just realized it right now. This is your constant. No matter what frame of reference you're in, everyone will always agree on that. Okay. Now, time and distance, right? Length and time, nobody agrees on it. Frame of reference from frame of reference. They all have a different say-so on what the distance is and what the time is. But the space-time interval, they all agree on, because it meshes it all up. Okay. Now let's take our guy that went 10 years to go to the nearest star at 80% the speed of light. All right. So that's 4 light years. Took him 5 years. Now that's according to Earth, prime, I. Okay. And so we're going to plug that into the formula here. We got time, right? We said we're only going to go halfway, though. We're just going to do it to the halfway point. We said it took 3 years for the spaceman and 5 years for the Earth person. That's 60%. And so that's right here. Plug the 5 years in for time, for I, right? Blue, blue. Over here we got distance, right? And how do we know what the distance is? 1, 2, 3, 4. We know it because that's how far the closest star is. And I just counted it out. And it's 80% of 5. If light goes that far and we're doing 80%, we're gonna go this far. So we plug that in. Now we got 25 and 16. This is where I messed up at, because these should be the T should be here and the X should be over there. That you should switch them around. But anyways, either way, you're going to get a difference. The difference here is 9. Okay, whether it was 16 minus 25 or 25 minus 16, it's still 9. The negative or the positive tells you whether the two people can affect each other. And like I said, this is a 9. Square it down to a 3, and guess what? How long it takes for these two to, remember how I said 3 years to get to the planet in the frame of reference of the space guy, and that's your answer, 3 years. Now you want to plug it in back into here, like the frame of reference of the spaceship, to see if it meshes up, right? And the frame of reference of the spaceman, he is the one who stood still. Remember, in anyone's frame of reference, if they're going at constant velocity, they, according to their frame of reference, they're standing still. Just like according to your frame of reference, you're standing still, even though the Earth is moving all around, all over the place, spinning, and you know what I mean, around the sun, around the galaxy. Galaxy's going through space. You know what I mean? You're not really standing still. No one's standing still. But everyone can say they are from their frame of reference. If they're going with constant velocity, which he is, so his distance is 0. Since he is not moving, the rest of the universe is moving. So x is 0. What's the difference between, and we know that S, we already figured it out, was 3, right? 3 years. So if you plug 3 into here, right, and this equals 0, whatever this is equals this. So this equals this, right? So there you go. 3, 3. They mesh up. You look at the very top of the board there at them two formulas. One is the space-time interval, and the other one is for a parabola. The formula for a parabola and a formula for the space-time interval are like exactly the same thing. But here's your x-axis. Remember the Minkowski diagram? Your time axis. I just have all 4 quadrants drawn. This would be 0, 0. And the speed of light. Remember, I just drew this area here. But this was the whole thing now. They do have these diagrams, and if you know about hyperbolas, this formula, you can buy graph paper. This is terrible how I did it, but they have parabolas drawn on there, a whole bunch of them, and you can use those. Like when I draw a line here, see how I drew this green arrow here, right here, see it? You would just, let's say you were taking your vector up to here, you're right on that parabola, you just follow it down, and whatever it says right here, because look how it's lower once it gets to the timeline for Earth, it's lower. So you know you're not going to have as many, you know what I mean? You can have, say, 3 years here, and over here, I mean, the person on Earth is going to have like 5 years, but the person on the vector, it goes all the way down to, say, 3 years. So you're going to slow down time. It's a lot easier than doing the math. Basically, I want you to remember back about the clock. See the spaceship guy? He's moving towards the right, okay? And as remember, behind him, the clock moves slower, but not all of them at the same rate. This one moves slower than him, but if you move further back, that one moves even slower than those 2 clocks. If you move even further back, that third one moves slower than those 3 clocks. And the same, the opposite in front of them. Right in front of them, the clock is moving a little faster. If you move a little bit more in front of them, that clock is moving even faster than those 2, and so on forever. See how the clocks are? This one's at noon, but this one's a little after noon. This one's a little bit more, a little bit more, a little bit more, because this is faster than this time. This time is slow. I want you to think of acceleration as the same way. If this guy was accelerating, it would get, the clocks behind him are slower and progressively get even more slow as you go back. And in the front, their clocks are moving faster, and they progressively move faster as you go forward. Just like here. The only difference is with acceleration, there's a really big difference. Yeah, time dilation with acceleration is a lot more than with just constant velocities differential. And the other thing is when I said how 2 people with different but constant velocities are looking at each other, that they're both perceive the other person to have slower clocks. Well, that isn't the case when it comes to gravity or acceleration. When one person looks at the other one of them's going to see a fast clock and one of them's going to see a slow clock. There's no misperception there. None of the equations are right in physics. You know what I mean? They all change because you have that uh, gravitational or accelerational force. We got the planet Earth here, see? And we got this big chunk of wood, almost as big as the Earth, right? Uh, just sitting there. Here's your time axis. Here's your spatial dimension axis. Let's say they're both moving at the same way through the space. So it's basically just they're both going through time, right? Because they're right next to each other. So relatively, they're still. Both the Earth and the big block of wood are both still. So the only thing they're doing is moving upwards through time. They're not moving through any other axis, any other dimension. But now I want you to remember, when you accelerate this way, you would feel gravitational force in the opposite direction, right? Now this Earth, its gravity is pointing towards the inside. It's pointing that way, right? Remember, when you accelerate, things behind you are slow, things in front of you are fast. Same with the opposite with the gravity. So this clock here on Earth is moving slower than this clock out here. This clock is moving fast, man. So when this log is, they're going along, you know, just standing there in space. They're actually both moving, but relative to each other, they're standing still. So they're only moving through the time dimension. This time is faster than this time, and this time is faster than this time. So what will happen is this will start to move more than this through time, through the time dimension. And what will happen to go into this position? Then it will start to go into that position, and then it will fall to the Earth. That's how gravity really works on a graph, is how it should be explained. And, you know, space doesn't exist, time doesn't exist, only space-time exists. You cannot tell if you're moving or standing still. There's no way to tell. You're only moving or standing still relative to something else. And no one can agree on it. No one can agree who's standing still, who's moving. No one can agree on distance or length. No one can agree on time between events. No one can agree on order of events. No one can agree on how fast time flows. No one can even agree on what is past, what is present, and what is future. Some people are in other people's past at the same time. What does that tell you? That tells you that you are not living in a three-dimensional Newtonian space and time. You're living in a four-dimensional Einsteinian space-time. One thing, space-time. That's why they say there's no such thing as space, there's no such thing as time. Because as individually they don't exist. It's like I said, time is not temporal. Think of it as a spatial dimension. You can't have, you can't have one dimension, and not have the other one. You need them all. So whenever you look out, you know what I mean, and you're standing on a planet and it's nighttime and you look out to the stars, you put your hand up and look at your hand and also look up at the stars. I want you to think your hand is actually something that you're seeing a fraction, even though it's like a quadrillionth of a second ago into the past. And when you look up at the moon, you know, you're looking like a second and a half into the past. And when you look at the sun, you're looking 8 minutes into the past. When you look past that to these stars, the closest star, you're looking 4 years into the past, 10 years into the past, 10,000. You go to galaxies, you're moving back millions and billions of years into the past. But you're doing it all at the same time. When you look at one galaxy or one star that's 4,000 years away from us, and then there's a galaxy behind that, you can't tell which is which. So you're actually looking at that galaxy too at the same time of something that happened a billion years ago. And maybe a galaxy to the right of it, they all look like they're happening at the same time, but that one happened a million years ago. What you see out there is not what is even there. Those planets and galaxies might not even exist anymore. That's why they say the illusion. It's just the illusion of reality.